In this problem, we have a bicyclist. He's traveling at a constant speed of 20 miles per hour for half a mile, and then he encounters a hill. The hill is a half a mile long, and his speed on the hill decreases as the velocity equals 1 over s to the fourth plus 4 miles per hour, where s is position. He crests the hill and then accelerates downward for a mile. We have the position velocity graph, and it shows the bicyclist's motion over the 2-mile trek. And we want to determine how long it takes him to bike those 2 miles. So this might be a little strange, having a velocity position graph instead of a velocity time graph, but we can still solve the problem. All right, so we're going to attack this problem by looking at the graph and dividing it into its continuous regions, because obviously this is an erratic motion problem. So we want to divide it into the sections that are continuous. And then we need to identify what we know and what we need to find so that we can choose the appropriate equation. All right, so if we divide the graph into the continuous regions, we have a region A here where it has continuous velocity. The velocity decreases in region B, and then increases in region C. All right, so now what equation do we use? So this is what we know. We know velocity and position. And this is what we need to find, time. These are the basic equations that we can work with. So what we need to do is find an equation that has those 3 variables in it: velocity, position, and time. Even though this is a strange setup where we have velocity versus position, we still need an equation that has all of these in it. So this is the equation that we're going to use, right? It has velocity, position, and time. Now we're going to have to rearrange it in a slightly different way in order to use it, because usually we take the dt over to the velocity time, but velocity is not a function of time. It's a function of position. So we need to take this velocity over here on the side of ds. All right, that is the most difficult part of this problem, choosing the right equation and knowing how to manipulate it. So we have our equation, and we have the dt over here by itself. We take the velocity over here on the position side, and then we divide it into the 3 regions: region A, region B, and region C. So each of those go from a particular position to a particular position. So we have those as the limits of integration. And then we just come up with the equation for the velocity in each of those sections. So section A, it's constant, so that's just a 20. Right, so we have 1 over 20. Section B, we're given the equation, so we put that equation in. And section C, all we have to do is come up with the equation of the line. Now, usually for simplicity, what I do is shift the origin to where the line starts, if the line is, not starting at the origin. So to do that, we have s minus 1, right, because it starts at 1. And then we just have the slope and the intercept. So once you shift it, the line equation becomes easy, and then you don't have to figure out, oh, where is the intercept way down here? You just shift it to where the line starts. All right, now 1 over 20 is not a difficult integral, and the last one is not too difficult either, but the middle one is. So what you can do is put that into a mathematical program, something like Wolfram Alpha, get it to integrate for you, and then once all of those sections are integrated, we get those values. And it turns out that at time that it takes the bicyclist to travel the 2 miles is 9.42 minutes.